In the previous lecture, we were discussing about the constitutive behavior of a fluid, and we tried to generalize the concept, but at the same time we tried to invoke a special consideration of a linear relationship between the stress tensor and the rate of deformation tensor, and that kind of linear relationship is valid for special types of fluids known as Newtonian fluids. So, we will start with that. So, we had tau ij is equal to tau ij hydrostatic plus tau ij deviatoric, and tau ij deviatoric we expressed asCijkl, which is a fourth order tensor, times EKL, where EKL is half del UK del XL plus del UL del XK. Now, as we discussed that if we want to describe the behavior of a fluid in this way, it will require 3 into 3 into 3 into 3, total 81 constants to specify the property of the liquid or fluid. But in general, we do not require that much number of properties. One possible way by which we reduce the number of properties required is by utilizing the symmetry of the stress tensor, that is tau ij is equal to tau ji. In addition, we also make use of homogeneous and isotropic fluid. So, homogeneous and isotropic fluid. What is a homogeneous fluid? A homogeneous fluid is such a fluid whose properties are spatially uniform, right. So, homogeneous means it does not depend on position. So, that means if you have a property of the fluid that is same at all locations, and isotropic means it is independent of direction. That means if you have a coordinate system and described by some coordinate axis, and let us say you rotate the coordinate system. For example, rotation, I am just talking about one type of transformation, it could also be translation, reflection, these types of transformations. So, if you rotate the coordinate axis, the property description with respect to the rotated coordinate axis will also be the same, because it is not dependent on direction. So, if that be the case, then the number of properties can be reduced further. So, let us try to form a scalar S which is homogeneous and isotropic. Let us say that our objective is to make a scalar out of this fourth order tensor, and what we have in our hand to convert the tensor to scalar is some vectors. So, how many vectors you require to convert this into a scalar? That is the first question. How many vectors you require to convert this fourth order tensor into a scalar? You require 4 vectors. Why? Because let us say you have the vectors A, B, C, D. Now, a vector is specified by one index. So, if you now writeCijkl into Ai, Bj, Ck, dl this stands for the vector A, this stands for the vector B, this stands for the vector C, and this stands for the vector D. Now if you write in this way, it means that there is an invisible summation over I because it is repeated, invisible summation over j from 1 to 3, summation over k, and summation over L. Finally it will have no index, so it will be a scalar. So this is a scalar, but we want it to be not just any other scalar but homogeneous and isotropic scalar. So first we will look into isotropy. So isotropic scalar means what is important? Let us say, so you have vectors, say A, B, C, D. When you have isotropic behavior, that means if you now rotate this vector system by some angle, then there will be no change in the property description. That means that the property will depend on the angle between the respective vectors which is preserved during rotation, but not the absolute orientation of the vectors A, B, C, D, but their relative angular position, because rotation preserves the relative angular position. Whatever was the angle between A and B before rotation, the same will be the angle between A and B after rotation. So that means that this will depend on only the angle between A and B. So angle between A and B is given by the dot product of A and B. So you can write this as a combination of, if you pair A with B, then you will pair C with D. How many such combinations are possible? You can pair A with C and then B will pair with D. You can pair A with D and then you can pair B with C. I have not written the full expression, I have just written what are the terms which will be governing the behavior. So these are the only combinations possible. See, A dot B and B dot A are the same. So it is not 6 but 3 combinations which are possible. Now it will depend on this combination, so we can say that because of the linear behavior, it is proportional to this times a coefficient alpha which you have to determine, this times beta and this times gamma, where alpha, beta and gamma are some coefficients which because of homogeneous nature do not change with position, they are not position dependent. Okay. Now we will write this expression in index notation. SoCijkl is equal to,Cijkl into Ai Bj Ck dl is equal to alpha Ai Bi. A dot B you can write Ai into Bi, right? Then Ck dk plus beta Ai Ci into Bj dj plus gamma Ai di into Bj Cj. Now I will show you a very interesting way of switching the indices. This I, j, k, l you can beautifully switch, you can switch from I to j, j to k, k to l, you can play with the indices. How you do that? You use an operator delta ij which is called as Kronecker delta. So what it does, delta ij is equal to 1 if j is equal to I and is equal to 0 otherwise. This is called as Kronecker delta. So you can write Bi is equal to Bj into delta Ij. Why? Because delta Ij is equal to 1 if j is equal to I. When j becomes I, Bj will become Bi and this will become 1. So you can see this is how you can switch index from one to the other. So using this we will write alpha Ai Bi is Bj delta Ij, Ck dl delta Kl. We are trying to write for all terms Ai Bj Ck dl because that is what is there in the left hand side, so that we will get a expression for Cij Kl. Then plus beta Ai Bj Ck delta, what will be this? Ik. Then dl delta jl plus gamma Ai Bj Ck delta, what will be this? What will be this? Then dl delta il, right? So from here what we can write? We can write Cij Kl is equal to alpha delta Ij delta Kl plus beta delta Ik delta Jl plus gamma delta Jk delta Il. Now how many properties have come? Magically from 81 properties you are having 3 properties, alpha, beta and gamma. Now we can reduce the number of properties even further by noting that tau ij deviatoric is equal to tau ji deviatoric. Because the stress tensor is symmetric, the individual hydrostatic and deviatoric components are also symmetric. So we will swap I and j. So first we will write Cij Kl. So alpha delta Ij delta Kl plus beta delta Ik delta Jl plus gamma delta Jk delta Il is equal to, now we swap I and j. So if we swap I and j, this will become alpha delta I and j, but delta Ij and delta Ji are the same. Delta is a symmetric tensor. So you can write delta ij again delta kl plus beta delta jk delta il plus gamma delta ik delta jl. From here what we can conclude? We can conclude that beta is equal to gamma, right. You can see that it will be beta minus gamma into delta ik delta jl minus delta jk delta il equal to 0. So that means you have beta is equal to gamma. So you can writeCijkl is equal to alpha delta ij delta kl plus beta delta ik delta jl plus gamma will be equal to beta delta jk delta il. So now how many properties are there? Two properties, alpha and beta. We will try to get a physical interpretation of these two properties. So tau ij deviatoric is equal to Cijkl into EKL. So what is that? Now you tell delta ij is, these are I and j are free indices because it is there in both left hand side and right hand side. So you really do not change I and j because you already have ij in the left hand side. So right hand side ij is the same as whatever is there in the left hand side, that you cannot change until unless you change the left hand side indices. Only indices that you play with are k and l. So delta kl is equal to 0 except when l equal to k, that is the definition of delta. So when l equal to k, this will be equal to 1, so EKL will become EKK. So alpha EKK plus beta delta Ik will become 1 when k is equal to I. So when k equal to I, this will become I, and delta JL will become 1 when L equal to J. So 1 into 1 into Eij plus beta delta Jk is equal to 1 when k is equal to j, and delta IL equal to 1 when L equal to I. So it will become Eji. So now what is Eij? Eij, this we have defined as half del ui del xj plus del uj del xi. So what is EKK? What is EKK? EKK is E11 plus E22 plus E33, right? E11 is del u1 del x1, E22 is del u2 del x2, and E33 is del u3 del x3. So del u1 del x1 plus del u2 del x2 plus del u3 del x3. This in short form we can write del uk del xk, right? But what is physically this? This is the divergence of the velocity vector. So this, as we have discussed earlier, relates to volumetric deformation of the fluid. This relates to the volumetric strain, the rate of change of volume per unit volume. So, alpha is related to the volumetric deformation plus beta. What is Eij and what is Eji? See, Eij and Eji are the same. So, Eji plus Eij is basically del uy del xj plus del uj del xi. So, just to write the same notation, we will write here del uk del xk. Now, physically what is this? Physically this relates to the relationship between the deviatoric stress and the rate of volumetric deformation. So, this is known as volumetric dilation coefficient. In most of the books this is given a symbol lambda, that is why I am just changing from alpha to lambda. It does not matter, but since most of the books use lambda as the symbol, that is why I am just changing it from alpha to lambda. This is called as volumetric dilation coefficient, because it is very clear that it relates the stress with the volumetric deformation. Okay. Now, what is this? What is this? Can you recall from kinematics of flow that what is this? This is rate of deformation. If I is not equal to j, that is shear deformation, and if I equal to j, that is linear deformation. But it is in general rate of deformation. So, you have the stress proportional to the rate of deformation. What is this proportionality constant called? Viscosity of the fluid. So, this beta physically is viscosity. Okay. So, this is tau ij deviatoric. What is tau ij hydrostatic? Hydrostatic stress is due to the pressure acting on the fluid element, because the hydrostatic stress is the only component of stress when the fluid is at rest. So, if the fluid is at rest, the component of stress that is acting on it is the normal component of stress, and that the normal stress is minus P. Why it is minus P? Because by nature stress is compressive, pressure is compressive, whereas tensile stress is considered to be positive stress. So, pressure is by nature a compressive stress, whereas by sign convention we take tensile stress as a positive normal stress. So, we write this as minus P into delta Ij. Why delta Ij? Because this is normal stress. This is 1 only if j is equal to I. J is equal to I means it is a normal component. When the two indices are the same, it is a normal stress. When j is not equal to I, this will be 0. Okay. So, you can combine tau Ij is equal to tau Ij hydrostatic plus tau Ij deviatoric. One term we had missed, I forgot to write this delta Ij, please correct this. I forgot to write this delta Ij here. So, this will be this times delta Ij. Yes, there was a delta Ij here. I just forgot to write it here. Okay. So, minus P delta Ij plus lambda del uk del xk delta Ij plus mu this is nothing but the Newton's law of viscosity for homogeneous, isotropic and Newtonian fluid, right. So, at every level, whenever you learn certain things, you have to understand that like things are possibly much more generalized than what is introduced for the first time. Like for example, if you are studying in high school and if you are taught what is a vector, what you will be taught? Vector is something which has magnitude and direction. Then you go to a little bit higher class, somebody will add a vector will have magnitude, direction and sense. Then if you go to a little bit higher class, somebody will add a vector not only has magnitude, direction and sense, it obeys the commutative law of vector addition, like either the triangle law or the parallelogram law. If you go to a class of abstract mathematics and algebra, they will discuss about n-dimensional vectors in a vector space which does not relate to any magnitude, direction or anything. So question is, which one is the most general one? Obviously what is taught in linear algebra as the n-dimensional vector space is the most general vector space that you talk about. So but always we start with the simplest one. So when you first studied Newton's law of viscosity, you studied tau equal to mu du dy. Just like for everything there is a version for children, Ramayana for children, Mahabharata for children, so that is Newton's law of viscosity for children. Okay. So when Newton's law of viscosity is first introduced, that is how it is perceived. Now that can be thought of as a special case of this law. So what it is basically talking about? It is basically talking about this part. So think about a flow when you have, say, in a two-dimensional flow it is like del u del y plus del v del x, the common symbols that you use for this. So if the flow is unidirectional, then you have only u component of velocity and then this is not there. So then that component of tau is mu del u del y. That is what is the Newton's law of viscosity that you have learnt in your earlier, I mean first exposure to fluid mechanics. But do not think that that is the most general form of Newton's law of viscosity. So for homogeneous isotropic Newtonian fluids, this is what is the Newton's law of viscosity. So never forget to include this term if you have a two-dimensional or three-dimensional flow field. Now we will discuss about the normal components of the stress. So first tau 1 1. So I equal to 1 and j equal to 1. So minus p delta 1 1 is 1 plus lambda del u k del x k plus 2 mu See, about viscosity we have many misconceptions, and one very common misconception is that viscosity is always related to shear deformation. It is not true. Viscosity may also be related to linear deformation. You see here this term, what is this? This is linear deformation, right? This has nothing to do with shear, but it also has a coefficient which is viscosity. So normal component of stress may also be related to viscosity. It is not related to viscosity only when the fluid is at rest. But if the fluid is under motion, then the normal component of stress is also related to viscosity. So it is not true that viscosity is just related to shear stress. Very loosely we say that viscosity is related to shear stress. Yes, it is related to shear stress, but it may also be related to the normal component of stress. Then tau 2 2 minus p plus lambda del u k del x k plus 2 mu del u 2 del x 2. Tau 3 3 minus p plus lambda del u k del x k plus 2 mu del u 3 del x 3. So now if we want to find out what is of minus what is tau 1 1 plus tau 2 2 plus tau 3 3 divided by 3, the average of the normal component of stress, that is equal to minus p, this 3 divided by 3 plus lambda, 3 lambda divided by 3 is lambda plus two mu into del u 1 del x 1 plus del u 2 del x 2 plus del u 3 del x 3, that is del u k del x k, that divided by 3. Okay. So these three added together will be del u k del x k. By definition, the left hand side is called as minus of Pm, where Pm is mechanical pressure. So this is the definition of a mechanical pressure. Mechanical pressure is by definition the arithmetic average of the negative of the normal components of stress. This P on the other hand is called as thermodynamic pressure. So what is thermodynamic pressure? Thermodynamic pressure is the pressure that relates the thermodynamic other parameters through the equation of state. For example, for an ideal gas, P is equal to rho RT, that P is thermodynamic pressure. So it which relates to other thermodynamic properties through the equation of state. So mechanical pressure which relates directly to mechanical forces in general may not be thermodynamic pressure. Okay. Now still there are many fluids for which a general relationship between mechanical pressure and thermodynamic pressure needs to be described, and that was described by something called as Stokes hypothesis. So just like any hypothesis, this does not have a proof, but this is found to be satisfied for most of the practical fluids. What is that? The Stokes hypothesis is that the mechanical pressure is equal to thermodynamic pressure. Now the question is that is it true always that the mechanical pressure is equal to thermodynamic pressure? To understand that, we have to appreciate the molecular origin of mechanical pressure and thermodynamic pressure. Mechanical pressure talks about the translational degrees of freedom, whereas the thermodynamic pressure includes all possible degrees of freedom: translational, rotational, vibrational degrees of freedom of the molecules. So when we say that we change a thermodynamic state, what happens? The translational, rotational, vibrational, all modes change and they eventually get translated in the form of mechanical pressure. Now that takes some time so that the system gets adjusted to the new change. There are certain types of fluids for which of course you can say that mechanical pressure and thermodynamic pressure is identically the same, like dilute monoatomic gases. They do not have rotational or vibrational other degrees of freedom. So, they have only translational degrees of freedom. Therefore, for dilute monoatomic gases, Stokes hypothesis is a law, it is no more a hypothesis, because it can be proved that for those for which there is only translational degree of freedom, dilute monoatomic gases. But for other substances, in general, this is not equal. Why? Because every system, when you create a change, a system takes a time to adapt to the change, right. It is true not just for materials or fluids, but for also us as human beings. So, if somebody wants to change us and we want to change ourselves, we cannot do it immediately, right. Even if you see in the morning you want to wake up, somebody gives you a wake up call or you get the alarming bell, still you cannot wake up instantaneously, right. It takes a time for you to adjust to this disturbance and respond to this change. This is known as relaxation time of the material. Now, typically the relaxation time is very fast, so that the material almost instantaneously responds to the change. But what happens if the material itself is changing at a very high frequency, changing its state at a very high frequency? Let us say that there is a bubble which is expanding and contracting very fast at a very high frequency. Then the bubble, when it changes its state from one state to the other, before that a new change of state has been imposed. That means the bubble cannot adjust itself to the change before a new change has come in. So, if you have a bubble which is changing its state very rapidly, then if the time scale of the change is faster than its relaxation time scale, it cannot relax to a new state. So, in that case you do not have mechanical pressure equal to thermodynamic pressure. So, Stokes hypothesis need not always be valid, but how often we discuss about such cases of very rapid change? Possibly very rarely. So, for almost all practical engineering purposes, this mechanical pressure is equal to thermodynamic pressure, that is why the Stokes hypothesis is such a popular hypothesis. Now, for the Stokes hypothesis to be valid, if you have Pm is equal to P, that means that this term must be 0, because this is the volumetric deformation, this is in general not equal to 0, therefore, you must have lambda plus 2/3 mu equal to 0. That means lambda is equal to minus 2/3 mu. Okay. We know that viscosity of a fluid is positive, therefore lambda is negative. So, what does it mean? What is the physical interpretation of negative lambda? It means that if there is a fluid, see the stress is what? The stress due to the component which is there associated with lambda is lambda del u k del x k. So, if this is positive, that means what? If this is positive, that means the volume is expanding. Then lambda negative means that the product is negative. That means if there is a fluid element which is already expanding, then the incremental amount of stress to stretch it further is actually negative. That means if it is already expanding, you do not require a positive incremental stretch to stretch it further, because then this component of tau ij is coming to be negative. Okay. The other important discussion is that there is a special type of fluid for which you do not care whether Stokes hypothesis is valid or not. That is a case when the flow is incompressible. If the flow is incompressible, then because of this equal to 0, you will have mechanical pressure identically equal to thermodynamic pressure. So, then it does not matter, then it is an identity. You do not care about the discussion on the validity of the hypothesis, it becomes an exact reality. So, on one side you have dilute monoatomic gases, on another side you have incompressible flows for which mechanical pressure is identically equal to thermodynamic pressure. You do not have to put any hypothesis to measure its exactness. Okay. So, we have been successful by the Stokes hypothesis to describe the property of the fluid by just one property, which is the viscosity. We had two properties, lambda and mu, but we have shown that lambda can eventually be written as a function of mu. So, only one property of the fluid, viscosity, is good enough to describe the state of stress of the fluid. So, with this understanding, we will now get back to the Navier's equation. So, this we derived in the previous lecture. This was the Navier equation, and we discussed that this is a very general equation. Only issue is that there should be no body couple, but the problem with handling this equation is that this has too many number of unknowns as compared to the number of available equations. So, now we will use the Newton's law of viscosity in place of this tau ij. So, what is this tau ij? Tau ij is equal to this one, with lambda is equal to minus 2/3 of mu. So, we will substitute that here. So, we will write del tau ij del xj. What is del tau ij del xj? Go to the first term, partial derivative of this with respect to xj. See, delta ij is equal to 1 when j is equal to I. So, xj will become xi. So, it will become minus del p del xi. Next term plus del xi of similarly lambda del uk del xk. Plus del xj of mu del ui del xj plus del xj of mu del uj del xi. Now, we will make a little bit of simplification to this term. What is the simplification? First simplification is, it is a homogeneous fluid we have considered. So, mu is not a function of position. If mu is not a function of position, this will come out of the derivative. So, you can write this as mu del xj of del uj del xi. If the second order partial derivative is continuous, then this is as good as mu del xi of del uj del xj. We swap this xi and xj, because for continuous partial derivative it does not matter with respect to which you differentiate first. And then this can be written as del uk del xk. See, this is a dummy index, this j. So, instead of j you can write whatever k, l, it does not make any difference. So, why we are writing it k here, you can see now that this term can be clubbed up with this term, because here also lambda is a constant, it is not a function of position. So, you take lambda out of this. So, del xi of del uk del xk plus del xi of del uk del xk. Here the coefficient is lambda and here the coefficient is mu. So, with this we can write the next step. So rho del uy del t plus uj del uy del xj and because lambda and mu are not position dependent, we can take them out and inside the derivative without any problem. So if we now club up these two terms together, it will be so this lambda plus mu, lambda is equal to minus 2/3 mu, so this will become mu by 3. Clearly the last term is important only for compressible flow, because for incompressible flow this will be 0. Okay. So this equation, what are the assumptions associated with this equation? So first we use the Navier's equation. There the only assumption was no body couple. Then so no body couple, of course you also have to add a body force that is there, so let us write that. No body couple, then the constitutive behavior, for that we assume a homogeneous isotropic Newtonian fluid. So homogeneous isotropic and Newtonian fluid. And finally we have assumed that the Stokes hypothesis is valid. So a fluid for which the Stokes hypothesis is valid is known as Stokesian fluid. So with these assumptions we arrive at this equation of motion, which is the celebrated Navier-Stokes equation. So again, what are the physical implications of various terms? The left hand side is mass into acceleration per unit volume. So right hand side is force per unit volume. This is force due to pressure gradient, this is the viscous force, and this is the force due to volumetric dilation combined with linear deformation. So for compressible flow this term is already there, but for incompressible flow this term is not present, and this is any other body force. There are special cases when the left hand side is equal to 0, that means the fluid has no inertia, that means the fluid is not accelerating, then that equation is known as Stokes equation. So this is a problem when a scientist does too many things. So you have Stokes law, Stokes hypothesis, Stokes equation, these are all different. Stokes law you have learnt in high school physics, that if you have a sphere which is in a terminal motion at a very slow velocity in a fluid, then what is this terminal velocity, how do you calculate the terminal velocity, the drag force and so on. That is Stokes law. Stokes hypothesis, mechanical pressure equal to thermodynamic pressure, and Stokes equation is the Navier-Stokes equation with the left hand side equal to 0. So all these three are different things. Okay. So now let us see how many unknowns and how many equations you have. So coupled with that you have the continuity equation, so now you tell how many unknowns are there. Unknowns. this equation basically there are 3 components, I equal to 1, 2, 3. So how many unknowns? What are the unknowns? Rho, P pressure, U1, U2, U3. These are like basically U, V, W. Okay. So you have 5 unknowns. How many equations you have? Here you have 3 equations and you have 4 equations. So this also does not close the system. In a special case, when it closes the system when the density is a constant or given. It may be a constant, may not be a constant, but some given function. So if rho is given or rho is a constant as a special case, then this system is closed. So then you can solve for the velocity field by using the continuity and the momentum equation. Momentum equation eventually becomes Navier-Stokes equation. However, if rho is not given, then rho is a function of what? Rho is a function of pressure and temperature through the equation of state. So rho is a function of pressure and temperature. This is equation of state. But you have increased another equation. You have got another equation, but you have increased another unknown. The unknown is temperature, right? So you wanted to solve for rho, but to introduce rho through the equation of state you involve an unknown which is temperature, and to solve for the temperature you need to solve for the energy equation. You get a governing equation of temperature, which is the energy equation in convection. So you require basically the equation starting from fluid flow to the equation of state and the energy equation, and sometimes the momentum and the energy equations may be directly coupled because the body force may be a function of temperature, and that happens in natural convection or free convection. Okay. So you can understand that what is the broad system of equations that we need to solve. We will come to the derivation of energy equation later on after we complete our discussion on the fluid mechanics relevant to convective heat transfer. Now finally, what are the challenges associated with solving this equation? First of all, this equation is a nonlinear partial differential equation, right? Why nonlinear? Because of these kinds of terms. This is actually the nonlinear term. Nonlinear coupled system of partial differential equation. This is not actually one equation, these are 3 equations, I equal to 1, I equal to 2, I equal to 3. So nonlinear coupled system of partial differential equation. This is point number 1. Point number 2 is you have pressure as a variable, but you do not have a separate governing equation for pressure. So you need to play certain tricks. You need to relate the pressure with the continuity equation to somehow get a governing equation for pressure, and that is not very straightforward. You have to do it through some numerical technique. So normally, because of this non-linearity and because of this particular typical nature of pressure for which there is no separate governing equation, you cannot solve this equation analytically. But for some special cases, for some special problems which we will discuss in the next lecture, it will be possible to solve this equation analytically, but otherwise for a general situation you need to use computational fluid dynamics or CFD to solve these problems numerically. So again, this course is not a computational course, but if you are interested to learn how to solve the Navier-Stokes equations in a computational platform, please go through any standard textbook on computational fluid dynamics, or you may also look into my NPTEL video lectures on CFD or computational fluid dynamics. The final note with which we will conclude today's lecture is, right, this is index notation, but how to write these equations in the normal XYZ system. So, because for problem solving normally we do not use the index notation but the normal XYZ system. So, we will write the equations in the Cartesian system. What I am doing is I am just writing this equation in normal XYZ notation. So, this is the x momentum. Similarly, we will write the y and z momentum. So, you see the elegance of using the index notation is that such big equations you can summarize through the index notation in this very compact form. So, to summarize, we have through these introductory lectures on convective heat transfer, we have related the fluid mechanics with heat transfer qualitatively, and then we have derived the basic equations of fluid mechanics which will be necessary for analyzing convective heat transfer. We will stop here today. Thank you very much.